Okay, welcome to the last day of the conference, and we're going to start with Raghu Mahajan, who came here all the way from Stanford. Thank you.
Thanks.
And then, he's going to tell us about annulus diagram with ZZ boundaries. Thank you.
Okay, thanks, Ted. I just wanted to begin by saying that I have had a fantastic week here, talking to an entirely new set of physicists, many of whom I've never met before, and it's a completely new subject for me. So I've had lots to learn. So I wanted to thank Ted and Martin for inviting me and having a wonderful time in Prague. Thank you. So I'm going to talk about this annulus diagram with ZZ boundaries. So it's about d-instanton effects. So in non-critical string theory, the d-instanton just gets called the ZZ instanton. So, and there will be about instanton effects in one of the simplest worldsheet models of the bosonic string. So in some sense, this is going to be a tiny baby version of Sergey's talk yesterday. So I hope it will be a bit of a review, and I don't know, hopefully you will still learn something. Okay, so just consider the statistical sum over all closed string worldsheets with no vertex operator insertion. So essentially, we are just taking sphere plus torus and so on, the multi-string version. So Z represents a multi-string partition function. And I have put here a Z superscript 0 plus Z superscript 1 plus so on. Z superscript 0 is the usual expansion, the sphere, torus, genus 2 surface plus dot dot and exponentiated. But we learned in the early to mid 90s that there can be instanton corrections. So even though we are summing over all closed string worldsheets, non-perturbatively, they can develop holes, and you can have some contributions even from open string worldsheets. And that I have here denoted by Z1 and dot dot dot. So this is the kind of thing we're going to study, this expansion. And since it's about instantons, we have to study the Z1. Okay, and I just want to write this using the logarithm of Z. So when we take a logarithm, Z0 is bigger than Z1. So you pull out a Z0, and then the next term is Z1 over Z0. Yes. One brain, one instanton. And then there will be a Z2 with 2 instantons, 3 instantons, and so on. Yeah. Yeah.
Is there any, you mentioned this geometry, is there any truly non-perturbative effect or which goes like 1 over G square, not the 1 over GS, correct?
No, this will be e to the minus 1 over GS.
Yes, but is there also some contribution of the kind 1 over G square?
That we will not be talking about in this talk. We don't know if those effects are there because there is no analog of the NS5 instanton in these theories as far as I know. So, by the way, Carlo, it's not necessarily one hole. One brain can mean multiple holes, but just with one brain. And the structure of Z1 over Z0, as Sergey also wrote, is e to the minus tension. Tension, or you can say action of the instanton. So this T is a quantity of order 1 over G string times some number n. It has been called the normalization constant in the recent literature. And it's 1 plus order G string, and there's a whole series here. It can, yeah. So yeah, so T and N both depend on GS, and that's actually the next point here. So our goal here is just to compute N. What is N? And more precisely, we will compute this quantity, N times T to the 1/2, because the G, as we will see, the G string cancels in this combination. And we want to compare, anyway, I'll talk about that later. So this is the goal of the talk. Okay. Okay, so I want to first tell you some story behind how I got working on this project and just a little bit of the backstory. So in this paper from July 2019, Shi Yin and 2 of his students, Bruno Balthazar and Victor Rodriguez, wrote this nice paper in which they computed ZZ instanton effects in the C equals 1 string theory. So that's a non-critical string with just one boson and the Leoville field. And they computed 2-point function of closed string. So it's just a 1-to-1 scattering, which is non-trivial in Leoville theory, to order GS exponential this thing. So they went to the next order, one more order than the one I wrote on the slide before. Okay, so they had a result from the matrix, which was it's just known. They could compute the result using the dual matrix quantum mechanics. But the string theory result had some unfixed numbers. They could not fully compute the string theory answer. But they sort of knew what it had to be. If you believe in the duality, then you know what those numbers have to be. But then Ashok Sen, just a month later, wrote this paper and a series of follow-up papers in which he showed how string field theory could provide an independent calculation of these numbers. And they match with the matrix quantum mechanics prediction. Okay, so in parallel, so that's the story from July and August. In parallel, in March of 2019, these authors, Saad, Shankar, and Stanford, wrote this paper called JT Gravity as a matrix integral. JT Gravity has a Lagrangian that doesn't look like any kind of a string theory or anything, but it's actually a particular limit of non-critical string theory that was recognized in this paper already. And this limit is basically in which the Leoville sector is semi-classical. And by that, I just mean there is a large coefficient in front of its action. And so since it is a limit of non-critical strings, it has ZZ instantons, ZZ branes. And in this context, it gives rise to the so-called transition between ramp and plateau features in this spectral form factor quantity at extremely long times of order e to the entropy of the black hole. So this 2D gravity theory admits some black hole solutions. And I don't want to go too much into this, but let's say they were studying dynamics at extremely long times. These are extremely long times for any system, but there is this feature which comes from random matrix theory called these ramp and plateaus. And it's precisely the ZZ instanton that's responsible for transitioning you between these two features. And what they noticed in this paper was that the one loop factor around the ZZ instanton is ill-defined. Well, they didn't notice it, it was known, so they couldn't compute it. They made the observation that this one loop factor around the instanton is ill-defined. So Douglas Stanford actually suggested to me that these techniques that Ashok was developing, which I talked about on the previous slide, to deal with the instantons in the C=1 system might also be relevant to this problem. Okay, so that's how I got into it. I started thinking about it, and I was visiting Bangalore in January of this year, and I was talking to Ashok, and we managed to make progress and write a couple of papers about this. Okay. So here are my collaborators. This is Chitrang Murdia. He's a PhD at UC Berkeley, and he's applying for postdocs this fall. As Dan Stefan Enicecu. He's from Romania. He's a third-year PhD student at Stanford University. And Ashok. This is a picture from the Fundamental Physics Prize website. Anyway, so in the end, I will talk about another upcoming work in which we also are working with Pronobesh Mehti, but I'll comment on that in the end. Okay, so about the strength of non-perturbative effects, something that was already mentioned. In fact, we knew that some effect of this order, e to the -1 over G string, has to be there just from the growth of coefficients in the perturbation series. So, the minimal string, these non-critical string theories were known before Polchinski even invented D-branes or discovered D-branes. And the point is that if you look at higher and higher genus in the perturbation expansion, the coefficients grow like to G factorial, where G is the genus, as opposed to G factorial. So these observations were made by Steve Schenker and other authors in the early 90s or late 80s. So the tension goes like G string inverse times this some constant D naught. And this is an important effect. Okay, so, and I already mentioned this before, N will turn out to be proportional to G string to the 1/2. So this combination is independent of GS and can be compared to a dual description. So this quantity is a pure number. It's just a real number or a complex number, and we can make a precise numerical comparison. Okay. Any questions about this? I will show that later. It will come. Yeah. In the C equals 1 string, actually, this was just G string to the 0. So it depends on which theory you're considering. So yeah, in these kind of string things that I'm going to talk about, it was just G string to the 1/2. Okay, so here's the worldsheet theory. Now I have told you a bit of a background, but now let's get to the exact theory that we're going to work with. So the matter sector is going to consist of a minimal model. It's a two-dimensional CFT labeled by two co-prime integers, P prime and P. And in general, it's a non-unitary CFT with a finite number of Virasoro primaries. And this is a matter sector, and it has C equals 1 minus this combination of P and P prime. And notice that this is strictly less than 1. And the simplest case, 2, 3, corresponds to the empty matter sector, which has C equals 0. So the 2, 3 is called pure gravity. It only has Leoville and the BC ghost, no matter. And well, then of course, since you haven't saturated the central charge to 26, the conformal mode of the metric remains dynamical, and it forms this Leoville CFT. And this Leoville CFT has central charge C anything bigger than 25. It's bigger than 25 by the amount this is less than 1. So the total central charge is 26. And then, of course, we have the BC ghost with C equals minus 26. Okay, so this is the worldsheet theory that we are going to study. This is the string theory. In the 80s and early 90s, it was understood by all of these authors and a lot more others that let's first set P prime to 2. So when it's 2, P, the above string theory is dual to an integral over 1 Hermitian matrix. Here I've denoted this matrix by M. It's an n by n matrix. So we have to just compute this integral. It depends on n. N is the size of the matrix. There's a T, is the 't Hooft coupling. It sits in the denominator with n. And we have some potential. The potential is some quadratic term, cubic term, and so on. The coefficients are gk. So this integral depends on n, t, and gk. And we divide by the volume of un here. That's just, in this case, is just a number. So we can do that. Yeah, maximal power of x can be taken to be P plus 1. Okay, and if P prime, this other number, if P prime is bigger than 3 and P is also bigger than 3, the dual theory actually consists of an integral over 2 matrices, not one matrix. And it has, these 2 matrices have their own potentials, which don't depend on the other matrix. And then there is a simple coupling term, M1, M2. And the point is, there's a lot that is known about these matrix integrals in perturbation theory. A lot is known and a lot has been computed. So we can really test our ideas about duality. And I want to say that this duality is actually one of the first realizations of 't Hooft's idea of casting planar diagrams into a string theory. So a gauge theory has matrices. Here we also have matrices, but they're just in 0 plus 0 dimensions. There are no space-time indices on these matrices. So you think of it as a gauge theory in 0 plus 0 dimensions. Okay, so any questions about this? Just the setup. So all we have to do is to compute this integral. And this integral should be equal to this log z that I was showing before. This log z, it's the same z. So the string computes a z, the matrix computes a z, they're supposed to be equal. The way I wrote it, the z will be equal to z. Yeah. Okay, so just a bit more of the background since, so this is a photo of a random surface taken from the website of Jeremy Bettinelli. There's a whole mathematical community actually studying statistical mechanics of random surfaces. And this is a sample that is taken by quadrangulation. So if you look, there are quadrilaterals here. So you can make up a discrete surface by picking some probability distribution. And so on the string side, that's what's happening. This is would be a sample of the string worldsheet that's contributing to the path integral. It's a random surface. You can weight it by its area and maybe some defect angles around each point and so on. So it's just some element of the ensemble of surfaces you're summing over. And that's it. Okay, so this is what like a typical one would look like. And so this is the string side, but also you can see, like Toph told us, the dual of this graph, of this quadrangulation, would be the Feynman diagram of m to the fourth. If you have a matrix with an m to the fourth interaction, this surface, and if you take the dual of it, those are the Feynman diagrams. So the history of this duality sort of goes back really to this intuitive picture. Yeah, the dual in the sense of graphs. Yeah, the graph dual of this picture. Okay, so I just wanted to show this because I like this picture. And so, right, so intuitively what it's saying is that 2D gravity, you can lattice it and take a continuum limit. It kind of makes sense, even though we can't do it in higher dimensions. Okay, so let's just get into it. Let's get into the matrix computation. And I again want to pause if there are any questions here. Okay, so let's go on. So we have to compute this integral. I wrote it before. Now let's specialize to the case where the potential only has two terms, x squared and x to the fourth. So it's even, so it's has some symmetry, some Z2 symmetry. Here is the original integral, matrix and this n and the Toph coupling and the trace of the potential. We change variables from, yeah. There's just the identity operator in the matter sector. Yeah, I'll come to it. Yeah. I'll come to that. Yeah. There's actually only one meaningful coefficient here, and that corresponds to, just to answer your question quickly, corresponds to the cosmological constant on the Leoville theory. So we convert change variables from the matrix to the eigenvalues because this trace makes it UN invariant. So the matrix that diagonalizes M drops out of the action. But in the process of doing this change of variable, you pick up a Jacobian. This delta of X is this van der Monde determinant, well-known factor, so it goes here. And now we are just left with n integrals over these eigenvalues xi. And here you just get b of xi. This van der Monde is very important. What it's saying is that there is no weight in this integral when the eigenvalues coincide. So the integrand just vanishes every time the two eigenvalues are equal. So that means that there is effectively a repulsive force between eigenvalues. And we will be interested in the case with G2 positive and G4 negative. What this means is that the potential looks like this. X and B of X. So this, of course, raises the question about the convergence of this integral and so on and so forth. Let me just suffice it to say that for now, we're just be interested in doing perturbation theory around a particular saddle point. So we don't really care about the overall well-definedness of the integral. For the purposes of this talk, we don't want to, it's just, let me not talk about that aspect of it. So G2 is positive, so it has a positive curvature here, but G4 is negative, so it eventually turns around. Okay, so before we get into the details, what is going to physically happen? Can everybody see this? So what is physically going to happen is that each of the xi's feels this potential. So let's say the xi's want to sit here in the center. It's a minimum of the potential. You can find a saddle point with the potential being like this, right? Like all the eigenvalues want to go here. But there is this repulsion from the van der Monde. They should not all be equal. So what ends up happening is that the attractive force and the repulsive force kind of balance, and the eigenvalues kind of fill out a droplet. Like in the large end, there will be a whole bunch of eigenvalues at the saddle point sitting in this minimum of this potential going up to some level. So that is going to be the structure of the saddle point. Okay. So of course, n will be taken to be large and so on to justify the saddle point approximation. Okay, so at a technical level, you introduce these two functions, the density of states, which is trace of delta of x minus m. Yes. I think he might not have turned on the mic. Oh, it's on now?
Okay,
yeah.
now. So the question is, why you are taking the potential going to minus infinity, which is a physical reason. Why you couldn't think, say, I take this and then I had a positive 6 power to the 6th in order to have a well-defined integral?
Well, the answer is that eventually, so in this diagram that I showed you with the random surface, you saw it was discrete. So in order to take the continuum limit and to match on to the 2,3 gravity, this is what you need to do. So I'll explain that a bit more as we go on. But the point is that the 2,3 model is dual to a limit of this problem. That's the eventual answer. So because we want to take a continuum limit, and it's called this double scaling limit for people who are familiar with this literature. I mean, that's what you're forced to do. I mean, there's no other option. Yeah.
It's possible, of course, also to take higher order potential, but you don't see this in the continuum limit. The potential becomes unimportant because the continuum limit concentrates just at the critical point, and you fall into universality class where the concrete form of the potential becomes completely irrelevant. So if you wish, you can add this positive 6 power. No, yeah, you can. But it becomes irrelevant in the continuum limit.
Yeah, that's true. Sergey's comment is completely correct. But I will add one caveat to that, that it's irrelevant for the perturbation series. If you want sort of a more non-perturbative definition, then those kind of things might be important to what the non-perturbative completion of the string series is. Because the matrix potential, we can define completely whatever we want. We can add an m to the 6th. But the question then becomes like, what is the string theory computing? Because in the continuum limit, we only get these sort of diagrams, right? We get the perturbation expansion. We don't actually know the full non-perturbative answer. At least I don't think it has been completely sorted out. Yeah, what do we do beyond perturbation theory? Like even instanton improved perturbation theory.
I have a question.
Yeah.
So you said like JT gravity is equivalent to some limits of string theory.
Yeah.
What is the interpretation of the JT gravity boundary condition?
Yeah, I was not going to talk about that, but just to answer your question, the JT gravity, you can study it on closed surfaces, then you don't need to put a boundary condition. But what people have studied it on geometries with a boundary. And there it corresponds in Leoville to the so-called FZZT boundary condition. So the FZZT boundary condition has a parameter, and that parameter corresponds via some Fourier transform to the length of the curve that people talk about in JT gravity.
Okay.
Sergey, is it okay, the comment I made, or you agree with that? Or
Well,
right. Yeah, right. That's what that's the kind of question I was asked. I was responding to, yeah. So I think we agree. Maybe, yeah, I think that's an open problem, is what I'm saying. Anyway, yeah, we can, talk about that more. So anyway, the technical way to solve for the saddle point in these matrix integrals is to introduce the so-called resolvent, is this trace of 1 over x minus m. Now, x is a general complex variable. You should think of it as complex, even though the eigenvalues of m are just real. And then the imaginary part of at this, as x approaches a real x plus I epsilon, is rho of x. So even though I've used x, in the first line, you should think of x as only being real, and second line, x is complex. Okay, the solution to the saddle point equations that corresponds to this thing has the following form. There's a piece in the resolvent which is completely analytic in x, and this is just related to the derivative of the potential. So in the potential, I put a g2 over 2x squared and a g4 over 4x to the fourth. So there's a piece, when you solve the equations, you just get a v prime here. And then there is a piece involving a square root with an x squared and a constant. And then there are these three numbers, a2, a0, and b. How are they determined? They're determined by the requirement that omega naught of x should fall off as 1 over x as x goes to infinity. Mike, yeah.
Should the omega 0 have any pole? Because
it doesn't have they have n poles here.
Yes, but the expression you are given has no pole.
But the pole becomes a branch cut in the large n limit.
Okay.
N poles combine to form this branch cut between minus b and b. Okay, so a2, a0, and b are determined by the requirement that the asymptotic behavior of this function should be just 1 over x. There are n things in the trace, so that n cancels this n. It can't be 2 over x or 3 over x. It has to be 1 over x. So then you can just solve. For example, the cubic term, it's easy to see. To cancel the g4x cubed, a2 needs to be g4. a0 needs to be this thing in terms of b. And b itself is determined by the g2, g4, and t by a nonlinear equation. So there's a nonlinear equation that determines b. And a2 and a0 are then just simply determined in terms of that. Yeah.
Okay, yeah. I'm not pretty convinced that the condition you gave is enough to specify B. Is like B just has to be like the boundaries of the part of the potential, like the edge of the distribution?
Yeah, B is the edge of the distribution, and it's determined by the condition that the residue of the 1 over x pole is equal to 1. So if you expand this, right, you start with x cubed. You have to expand the square root at large x. So you pull out an x, you get a 1 minus b squared over x squared. So the first three terms would be x cubed, x, and something with 1 over x.
And so that's two conditions.
Sorry?
That's two conditions.
That's three conditions. That's vanishing of x cubed, vanishing of x, and the residue being equal to 1.
Oh, residue equals 1, okay.
Yeah, because of it's important that the residue is exactly 1. That's like normalizing the density to 1. Right? Because if you have n eigenvalues, the trace gives an n in the numerator. That cancels this n, so it's precisely 1 over x at large x. So those are the three conditions. Okay, thanks for those questions. It's useful to go through some of these technical details. Okay, so here is the solution again. I just wrote it again. And the resolvent equals 1 over x as x goes to infinity on the first sheet. Note that it's important to specify the sheet because there's a square root here. So this minus sign could have been turned into a plus if you went to the second sheet. And it's not really required to go like 1 over x on the second sheet. That's okay. And I think these part I already said, the piece involving the square root determines the density because the density is the imaginary part of omega. And the imaginary part will only come from the second term. And notice that if you set G4 to 0, then it's just a Gaussian potential with positive Gaussian. And then you should recover the Wigner semicircle. So A2 vanishes. A0 is a number. You just get a square root. So that's the Wigner semicircle when G4 is 0. Okay, and I just want to say the final equation is a nonlinear equation that determines B. Okay, so you can take the saddle point, plug it back into the action, get the saddle point free energy. The free energy will be order n square. You can do perturbative corrections and so on and so forth. So the saddle point that you get this row, you just completely determines the planar free energy and also the perturbative expansion. But we want to go beyond and consider effects from, in the matrix model, what are called the one eigenvalue instanton. What this instanton is just an integral. So it's just another saddle point of the integrand. So we have one saddle point, and now we want to find some other saddle point. Okay, so for that, it is useful to introduce this quantity called the effective potential. And we have this Vandermonde downstairs, delta square. We can exponentiate it. We can write it as e to the 2 log delta of x. And then look at the terms in which xi participates. I is some fixed eigenvalue of the potential minus this repulsive term. So there's a logarithmic potential. And so this is just the effective potential. There's an attraction due to the V and a repulsion due to all the other eigenvalues. Now there's this annoying absolute value. So it's useful to actually introduce a holomorphic effective potential like so. So you just replace the sum over J with an integral over the density in the large N limit. And this is the definition of the so-called holomorphic effective potential. And what we're going to do is basically to look for extrema of V effective. So that is where eigenvalue can sit, because this function can have non-trivial zeros.
So holomorphic because you are thinking of X as complex.
Yeah.
And so you are looking for complex saddles.
Yeah.
Also because you have a logarithm which has no modulus.
Yeah, so the way why I'm calling it holomorphic is just because I've removed the absolute value from here.
And you take X complex. Okay.
X complex, yeah, exactly. Okay. So a more general potential, if we don't just have the quartic, so far I just showed the equation of the quartic, the density of states, which is the piece of omega involving the square root, always has this b square minus x square times a polynomial, m of x. And if you work out the math, the derivative of the effective potential actually has the same polynomial in it. So the density and the derivative of this holomorphic effective potential are very closely related objects. Okay, so I just put here a theta function to just emphasize that the density is supported on real x between minus b and b, whereas this quantity here is a holomorphic object with x being complex. And again, m of x is just determined by the requirement that omega naught of x goes like 1 over x on the physical X sheet. And so one eigenvalue instantons correspond to the extrema of V effective with x being outside of the interval minus b to b. In other words, these one eigenvalue instantons are nothing but the zeros of m of x. So we can already see here from the previous thing I showed you, m of x is this quadratic thing, and it just has a zero. So if we look at the effective potential, what it does in the quartic case is that unlike the potential, which looks like this, the effective potential is 0 from minus b to b, or it's a constant, and then it does that. So this is V effective. And this maxima here is not the same as this maxima here. It's just something else. So this is the effective potential. It's flat here because that was the saddle point condition, that there is no force on an eigenvalue when it sits here. So, okay, so those are the one eigenvalue instantons. And okay, so that's it. Are there any questions about this? Yeah.
So are you saying that you can only put an instant in the top of the effective potential? Because
yeah, at the top.
Otherwise it's not
Well, because see, we are just solving some saddle point equation, some derivative of something equal to 0, right? We have e to the v of x plus log delta of x. Okay. And the saddle point by definition is just ddx of that thing equal to 0. So there is no tunneling instanton because it's not a quantum mechanics, it's just an integral.
So you can just put
one
isolated
here.
eigenvalue on the
Yeah, you can put maybe an order 1 amount. You could put maybe 3 or 4 or 5.
Oh, is that
Also.
true? So because you don't worry about the repulsive force.
Sorry?
There should be a repulsion.
Yeah, you can take that into account. If you put like 5 eigenvalues here, there will be a little 5 by 5 matrix integral that you have to do here.
Okay,
so the repulsion between the eigenvalues, if you put multiple ones here, has to be taken into account exactly. And we did that in the second paper, which was about multiple instantons.
Okay, thank you.
Mike?
Sorry, can you repeat why there is no tunneling effect?
It's not a quantum mechanics problem. So there is no time in this. There are no trajectories. It's just an ordinary integral over lots and lots of variables. The saddle point for that is just the derivative of something equal to 0, right? So the saddle point is just at the top. It's not in the C equals 1 case, it's a matrix quantum mechanics. Here is just a 1,000 by 1,000 matrix, million variables. That's it.
So this only really gets contribution only from the saddles of the potential, and that's all. There are no other classical solutions essentially.
Well, in some sense, the saddle points are the classical solution.
Yeah. But if you also at time, there would be also another classical solution that would be the tunneling.
Right.
Yeah, but here you don't. I see.
There's
Okay,
no time.
thanks.
Okay, so let me now explain what this double scaling is and what it does, and because I think it's important. So let me write this equation.
Sorry, my problem is when you have you have a extrema in a problem which you want to treat with saddle approximation. It happens that not all the saddles are relevant because you in the space you cannot deform your original integration contour.
Yeah, it's good. You're asking all the right questions. I will address the contour issue in a later slide. Yeah. So it does contribute, and it's understood that it contributes. Yeah. Okay, so let me draw another figure. So this left-hand side of this equation as a function of R. So G2 is positive, so it has a linear piece, but then it has a G4R squared, there's a negative piece. So it eventually turns around, and it has to be equal to T. T is positive. So we have to solve this equation. We have to intersect it with 16T, the line. So first of all, notice that there are multiple solutions, but we have to take the branch of the solution that's continuously connected to 0. That goes here. So we pick this root. So that determines R, which is just B squared. Now, what happens? As you increase T, so the right-hand side, as you increase T, eventually this is going to hit the maximum of the left-hand side. And what this means is you're not going to have a real solution for B. So approaching this limit, this is the critical value. If T becomes bigger than G2 squared over 12 absolute value of G4, we do not have a real solution for the cut endpoint. And that approach towards that parameter value defines the double scaling limit. Okay, so the geometry of this is important. The fact that G4 was negative, so this had a maximum. And what is becoming complex at the double scaling point is just this B, this endpoint of the cut. Okay, so another important point. So because this B is entering into the saddle point, which is entering into the planar free energy, the function of the planar free energy as a function of, let's say, G4 hits a singularity as a function of G4. So we know that planar, if you pull out the n squared, the perturbation series is a convergent expansion. So you can sum that, and there's like the first singularity closest to the origin in G4 is precisely at this value of G4. G4 is like negative G2 square over 12T. So it defines the radius of convergence of the G4 perturbation series. So you take large N, you do a G4 perturbation expansion, this is the radius of convergence. If you were to do the planar diagrams using perturbation theory in G4. So what you're saying is that there was this sum over graphs, over all planar graphs, and now it's not converging anymore, it's diverging. What it means is that the higher and higher diagrams with more and more vertices are becoming important. So more and more vertices are becoming important, which means that your Feynman diagrams are getting really big, which means that you're approaching the continuum limit. So it is only in this limit where you allow for lots and lots of vertices, the Feynman diagrams with lots and lots of vertices to contribute, is you recover the continuum limit of the string. So that's why this double scaling is important and so on. Okay, so now I just want to make a comment. So this with the quartic, everything was simple and explicit, but when P is larger than 3, you can take the potential to be even of degree P plus 1. So the next case would be 2,5 with a degree 6 potential. And now actually there are various possible double scaling limits. You have G2, G4, G6. You can approach various kinds of limits, and this function will be even more complicated, and you have some freedom. Now, we would really like to study on the string side the standard Leoville Lagrangian with only the cosmological constant term turned on. We don't want to turn on any other operator in the Lagrangian, and it was figured out by these authors what that means on the matrix side. Yeah, there's a question.
So I think that usually we say that the double scaling limit is a limit where you go send n to infinity and then scaling as an g to the send G4, I think in your case, to the critical
like
value.
this, yeah.
So, but in your case, so what is T in this picture?
T was something that is sitting in the action. It was N over T, G2 over 2 x squared plus G4 over 4 x to the 4th.
So what is the original? So I think I just missed where you introduced T.
Where?
T. Yeah,
T is just in the exponential. It's in the definition of the integral. It's the 't Hooft coupling, right? So when we write in a gauge theory, we have a 1 over G square out front. We write G square as N over lambda. Here I have written G square as N over T.
I see.
So
I
T, you should think of it just as the 't Hooft coupling, like you would normally.
Thank you.
I think you can scale a lot of these out, and essentially there's only one parameter in the game, which is how close you are to the top here. So essentially only that combination sort of matters. Right, so how close R is to this value, or how close T is to this value. You can put it in many ways, yeah. Yeah, the reason I put all these things is because if you don't put them, you go to higher order potentials, like it's just convenient to have everything explicit, and yeah.
So when you do this double scaling, it's going to be dual to Leoville theory, right?
Yeah.
So how does the on-shell actions relate to each other? Like the on-shell action for the matrix model will be equal to Leoville action. It's supposed to work like that, right?
Well, yeah, it will be if you identify the right saddle point on the Leoville side. So here I told you about there's an integral on the matrix side. You find the saddle point, you plug it back in, you find some free energy F0.
Yes.
You have to do the same thing for the sphere.
Basically, it should be like one of those. Basically, you need to know the topology of the surface that you put the
right. So you know the n squared term in the free energy will come from the sphere diagram, like Teresa was talking about.
Yeah.
So just by power counting, you know that it has to be the sphere diagram, the empty sphere with no insertions. And in Leoville theory, you can actually compute it, like Teresa talked about, and we also wrote a paper.
So is it like this complex, like a complex metric that you were
right? So in this case, when you take the Leoville central charge going to plus infinity, the saddle point is this funny complex metric with a minus minus signature.
What about the more usual saddles, like puncture spheres and?
Well, they're not relevant for computing F naught. If you were computing some correlation function, then they would be relevant.
I see.
Because I'm just computing the integral, which is the free energy,
I see.
which does not have any vertex operator.
So what I'm asking is that in principle, I can compute these quantities using metric, like a simulating metrics model, right? Like say that I want to evaluate on-shell action of the Leoville theory on this, like one of those Riemann surfaces, and that will correspond to some correlator in the metrics model side, presumably.
Yeah,
on the right side.
That's true. Yeah.
Then in principle, you can just simulate these metrics models and get this.
That's correct. You would have to go to the appropriate genus diagram.
I see. Yeah. Thank you.
There's a question there. There's a question? Oh, okay. So anyway, this is the double scaling limit. And so what you need to do more precisely. So epsilon now, I have introduced the one parameter which tells you how close you are to the double scaling limit. So this was X. What you need to do is you need to go very close to this endpoint. You just go to minus B, look really close there, and define a new variable, this energy. So energy of order 1 means X is very close to the left endpoint. And this Moore-Seiberg-Staudiker result is that the density of states should look like this. So the density of states will only be supported now for positive E. And it has the sinh times P of arc sinh form. This is a polynomial in square root of E. It's not obvious, but it's just some trig function that you can expand out, and it's a order P or P over 2 polynomial in energy. And e to the S naught is the new genus expansion parameter. So we take n to infinity and epsilon to 0. So n is going to infinity, epsilon is going to 0 with this combination held fixed, this P over 2 plus 1 with a specific power. And this exponent is called the KPZ exponent. So what happens is that you take n to infinity, epsilon to 0, and this combination becomes the new genus counting parameter. I've written it in a funny way to agree with the JT gravity literature, but essentially this is proportional to the 1 over the string coupling. Okay, so this 28 is an input from the Leoville theory because we want to approach the double scaling limit in a specific way. We don't want like Leoville deformed by some relevant operator or something like that. Okay, so when P is 7, this is what the effective potential looks like as a function of energy. So now it's the rescaled variable. It's just 0 to here. So notice that energy is 0 here, and it's like negative. So you hit a maxima, then a minima, and then a maxima, and down again. So it's more complicated than just a single maxima. So you have these 3 maxima. So these would be like 3 different saddle points in principle. And you could put like 5 eigenvalues on the first one, 7 on the second one, 3 on the third one, whatever you want. And you can compute all of those contributions. So this is what it looks like. And as P becomes larger, you get more and more oscillation. So if P was 9, you would have 1 more oscillation. P was 11, you would have another one, and so on. And JT gravity is basically P going to infinity. That's JT gravity. P goes to infinity. Okay, so this is the effective potential. And it's now very simple. You look at the extrema, the first 0. So let's just focus on this first one. As you move towards the negative energy, find where this first extrema is. Well, we had the explicit form of rho of E. And I showed you on the previous slide that rho of E is very closely related to the derivative of the effective potential. So you only need to find where this function is equal to 0 for negative E. It's funny, but there's a cinch, you have to take care of some i's and so on. But you find a negative value of E, so ignore this kappa, it's just some irrelevant order 1 number. It's like negative 2 sine squared pi over P. And we know the effective potential, we know this everything, so we can just compute the potential and the double derivative at that saddle point at E star. And just some very concrete function in terms of P and sine, that's only P that's important here. Okay, so we know the height of the potential, we know the curvature of the potential. We can just now compute the compute the contribution. So this slide is a repetition. Z0, Z0 with no instantons come from the saddle point where all the eigenvalues are here on the cut. Z1 comes from eigenvalues n minus 1 here and 1 here. So again, I just rewrote this to have no instanton plus 1 instanton, take the log, isolate these things. And here is the answer. So you have exponential of minus the action times a Gaussian integral over the energy variable. That's just like this, 2 pi over square root. I will explain this I over 2 in a bit. And the non-trivial part of this whole calculation is this extra factor here, this minus 1 over 8 pi E star. If you want, I can tell you the details about this factor later, but it's not super relevant for the main message of the talk. So just believe me, there is also this factor, but the first two terms are kind of intuitive. There's this Gaussian integration term and just the on-shell action term. So why there's an I here is because you notice that from the graph that the first guy I'm looking at is always a maximum. So since it's a maximum of the potential, it gives an I. And the 1/2 I will explain on the next slide. So now we just compare this Z1 over Z0 to e to the minus t times n. So this V effective of E becomes the tension, and this everything else becomes the normalization constant. You just plug it in, and you find this value for this quantity we were looking at. So n times t to the 1/2 is just some square root of 32 pi, cotangent pi over p, square root of p squared minus 4. Yeah.
So you're saying that when p is more than 3, there are several kinds of instantons, and then you chose one.
We chose one particular one for this slide.
Why did you choose that one?
In the second paper, we did the most general calculation. So it's just for illustration, I chose this one.
Is this something that dominates or just pick up?
No, you can consider the most general instanton configuration and compute this. It's just the simplest case, so I like presenting the simplest case.
Okay. So are you going to explain that in the interpretation of the instanton in the string picture?
In the string picture?
Yeah,
Yeah, that's the second part of the talk. Yeah. Okay. Question? So this is the result. It's a precise number with an I and a square root of 32, and we want to get this precise number from the string theory.
So I just wanted to say that it's now about 10 o'clock, so you have about half an hour to finish the talk. So
okay, thanks. I guess I've been going slow to interact, but the string part will be easy because Sergey already covered it yesterday as well. So anyway, but are there any questions about this?
Will you sum eventually over the instantons? Or?
So we don't have a proposal for what the full answer for the Z should be. So you can think of this as just analyzing the integrand. You know, you're taking the integrand, you're looking where the various critical points are, and you're doing sort of the integral over the Lefschetz thimble of that saddle point. But the question that I was answering to Sergey, we don't know what the defining contour is. Because you don't know that, you don't know what linear combination of the steepest descent contours is homologous to the defining contour. So in principle, you have all the data from these n's and e to the minus t's. And if you had the integers that define the homology class of the defining contour, you could just put everything together and get the answer. But the problem is that the non-perturbative definition seems to be a bit mysterious in these models. So you can do some local analysis around each saddle point. The situation is slightly better for this case. I show it here. So E is positive on this side. So, you know, naively, you might have thought it's a Hermitian matrix integral. So you have just the real axis as the contour of integration. But one proposal that has been made is you come in from this side, you stop here at the critical point, and then you turn the contour to follow the steepest descent contour in the complex plane. So this is the energy plane, complex energies. So this is one possible defining contour. And that is why you have the factor of a half that I showed on the previous slide, because you're just integrating only half of this contour. But this is not like set in stone. Like there could be a different contour that you could integrate over and stuff. But the point is there is a precise match on the string theory side. So whatever contour you want to pick on the matrix side, the ZZ instantons are such that you could make the same choice on the string side. So you still have a match in that sense. Yeah.
Can I? Maybe I can make a comment concerning this non-perturbative ambiguity, because it's related, it's some ambiguity in the definition. Actually, we know in other contexts, but which are related. For example, take topological string theory. And we know that in some cases, these theories describe some limit of topological strings. And in that case, we also have an ambiguity in the non-perturbative definition. It was understood that that has important physical and mathematical meaning. So, there is kind of a bundle which describes, for example, topological string partition function, and this partition function is a section of that bundle, and the non-perturbative definition ambiguity is related to kind of transition from one patch to another, and
okay.
Think that it's irrelevant, it should be fixed once for that it's really something physically important.
Yeah, I agree. But I think what should happen is if we fix the non-perturbative ambiguity by picking a contour, let's say on the matrix side, the string theory, we should have like an independent, object that reflects that ambiguity. So I agree, we can do various things on one side, but if the duality has to be correct, then we should also have the corresponding things on the string side, independent definition of the things on the string.
Yeah, sure.
Yeah. Okay, thanks for the comment. Anyway, so I guess we had a lot of questions and Ted warned me about the time, so let me go on. So now I would like to answer Yuji's question about reproducing this from the string theory. So here is the action of Leoville theory. It's an action over a scalar field phi, exponential action. Action has the kinetic term. There's a linear dilaton term, which changes what you mean by the stress tensor of the theory. So the central charge is shifted by q square. And then there is this cosmological constant term. You should think of this as mu times the area of the worldsheet. E to the 2b phi is like the square, it's the square root of the physical metric. This g is some reference metric, and root g times e to the 2b phi is the root g of the full metric. Q is b inverse plus b is some parameter less than 1. So the DDK scaling or the KPZ scaling tells us that a surface of genus G is weighted by this number, mu to the Q over B times chi. Mu to the Q over B is the G string then, is the string coupling. There are vertex operators in this theory which look like e to the 2 alpha phi. You can think of alpha as some complexified momentum. And we have a DOZZ formula for the 3-point functions on the sphere. And there are two kinds of branes. There are FZZT boundary conditions labeled by a parameter, cosmological constant, boundary cosmological constant. We are not interested in those. That was the answer to Charles' question. And then there are ZZ boundary conditions, which represent instanton effects, and they carry a discrete set of labels. The discrete set of labels correspond precisely to the maxima and minima of that potential I showed you. So for p equals 7, there would be 3 ZZ branes. Okay, so we have these perturbative expansion. I'm just repeating this. And then there are non-perturbative effects represented by opening non-perturbatively a hole on the surfaces. And you have the disk topology and so on. So T is the tension of the ZZ brane. Roughly speaking, it should be the empty disk. And a direct computation of the empty disk and comparing it to some quantity on the sphere has issues with unfixed SL2R. And actually, Sergey had a paper long ago about this. But I still think that a completely independent worldsheet computation of the ZZ tension should be done. And maybe we'll do it in a future work. And well, there has been some other work. Well, this was a paper from long ago, and there's a recent paper by Lawrence Eberhardt and Sri Pal that tries to deal with this unfixed PSL2R on the disk. But anyway, that's something else. Yeah.
Is there some simple reason why the FZZT brain should not participate as other kind of corrections?
FZZT brain, you should think of it as a higher DP brain. So it's
right,
part
like
of the
space
in-state.
filling, yeah.
So
they cannot be created like
right. So they are not. They will be. They are not instantons.
So
they're like particles, like.
Okay.
They're like d particles, so you cannot just have like.
Okay. So they're not selected by the path integral somehow. I mean,
yeah. Sorry.
So you can make a path integral where this FZZT brain don't give.
Yeah, like this free energy calculation just doesn't have the FZZT brain. If you wanted to just like compute what Charles was asking about, some JT gravity Z of beta, that Z of beta would be dual to mu b on the FZZT, and then you would have that. So n that we want to compute is the exponential of the empty annulus, like also in Sergey's talk yesterday. So it's e to the disk plus annulus. So, well, the good thing is the annulus partition function is known. So let's take Leoville theory and work with this so-called 1,1 ZZ boundary condition, which corresponds to the first maxima of the effective potential. This character is just the identity character of a particular central charge. You have eta to the -1 that counts the descendants. And this -1 subtracts out the level 1 null state. The partition function of the matter CFT also has a discrete set of labels called these Cardy boundary conditions. And we pick the simplest one, which again corresponds to the identity character for that particular value of the central charge that the matter CFT sits at. For 2,3, Z matter is just equal to 1. There's nothing, the sum is canceled by this eta. So you can just think of Z matter equal to 1 for this case if you set P equals 3. And there's a contribution from the ghost, eta square. You put it together. Q is e to the -2 pi t. T was the time in the open string channel. You find e to the 2 pi t -1 times this infinite sum. The infinite sum is not very illuminating if you stare at it, but it has this leading behavior. As t goes to infinity, there are two terms that are important. There is +1 coefficient e to the 2 pi t -2. Everything else is exponentially suppressed. And that's a problem because we have to integrate this f of t from 0 to infinity over the modulus of the cylinder. So there's an infinity coming from this upper limit. There is no problem near the lower end because these theories don't actually have a closed string tachyon. So this +1 means there's a bosonic, well, L0 equals -1 mode. So there's an open string tachyon. And there are two fermionic 0 modes. So we have to deal with them. Otherwise, this just n doesn't make sense. Yeah. Maybe we can use the other mic.
Fermionic 0 mode of BC system?
Yeah, of the BC system. I'm going to show you on the next slide. So here are the set of states that you should worry about. There are 6 states I have written here. The red ones are the ones in Siegel gauge. C1 on 0 is a bosonic state with L0 -1. So that's giving the e to the 2 pi t. The 0 and the C1, C -1 on 0 are L0 equal to 0 states. They are Grassmann odd states, and I've called them here P1 and Q1. So the red states are the ones giving the terms on the previous slide. E to the 2 pi t, -1 from here, -1 from here. So e to the 2 pi t -1, -1. Okay.
So you are taking the full full spectrum of the string, not only restricting to ghost number 1.
Yeah, this is
usually, as I understand, usually people restrict to ghost number 1. So you are going those.
Well, this is just in Siegel gauge, so we have everything. The usual worldsheet partition function computes it in Siegel gauge. So this state is C1, C minus 1 is in Siegel gauge, and it makes a contribution. Okay. Actually, so the point that Ashok Sen realized in his work following Shi Yin et al.'s work is that this P1 and Q1 should be replaced by this d psi integral. Psi is an out of Siegel gauge state, so you have a C0 here. It has L0 equal to 0, but this is what you should do, and you should explicitly divide by the volume of the gauge group. So the psi field is what you have to do. So you have to make this replacement in the path integral. Throw out the P1 and the Q1 and replace it by psi over d theta. So let me just dwell on this because this is like the main point. So the other details we can skip. This quote thing is my term. So you have to unfadif Popov this thing. What does it mean? Usually in a gauge theory, we start out with an integral like this. There's an integral over field divided by volume of the gauge group. And the volume of the gauge group, there's a local rotation at each point in space-time. So there's U1 to the number of lattice points. Here we have an open string field theory on just a d instanton, which is a zero-dimensional world volume. So the U1 is just U1 at a point. It just has a completely finite volume. There's no need to gauge fix. And so there's no need to gauge fix. Why? Because the gauge group volume is just some 2 pi or something, right? So you shouldn't have gone in this integral anyway. And the fact that the P1 and Q1 has no action, it's just e to the 0 P1, Q1, is because that gauge fixing was bad. Okay, so that's it. Now, there's another point, which is, why don't we hear about this subtlety in...
Sorry, what was wrong about the gauge fixing in this case? I didn't understand.
So yeah, so I can explain that a bit. So for example, I was going to say that. So usually, why the d instanton is special? If you have a d0 brane, first of all, the 0 will be replaced by a k. There's a continuous momentum label on these things. We don't have that because we just have a d instanton. So usually if you have a 0 mode, you have a 1 over k squared plus m squared propagator. You can avoid the singularity at the 0 mode by just deforming the contour in the k plane, like with the Feynman I epsilon. But you don't have the Feynman I epsilon here because there's no k on the world volume. So that's why the infrared problems are more harsh, because it's just a discrete state. It's just one state that is a 0 mode. You don't have those things available. And related to that is, what would this term have been on a D0 brane?
So I can also add some comments.
Yeah. Please.
Okay, so I mean that's true, but like I think Martin's question was why the gauge is failing here.
Yeah, so I'm going to explain that.
Oh yeah, you're going to explain. Sorry.
Yeah. So what this kinetic term would have been, this exponential of minus psi square, it would have been negative d mu a mu minus psi square. If you had a gauge field on the D brane, if it was a D0 brane, and the gauge transformation law, if you just work it out, is a mu goes to a mu plus d mu epsilon, and psi goes to psi plus d square epsilon. So this combination is gauge invariant. So if you had momentum, you could use this shift to set psi to 0. That is Siegel gauge. You're setting psi to 0. Psi is a field that's out of Siegel gauge. You use this gauge invariance to set it to 0. But there is no momentum. So psi is by itself gauge invariant. A mu you don't even have anyway. So that's why the gauge is breaking down, because the gauge the field psi is sterile under the gauge transformation that you would have used to get rid of it. And in the usual story, you set psi to 0, and you get this, this d mu a mu square term, which is what you usually get in Feynman gauge or thing in string theory. And then the P and Q would just have been the Faddeev-Popov ghost for that gauge fixing. So
another way of saying this, that like this, if you have done the Faddeev-Popov, you will find a determinant, like determinant of a, determinant will just vanish, right?
Right. So that's coming from the fact that these are 0 modes.
Exactly.
So it's e to the 0. Yeah. Okay, so that is basically at the heart of the matter. One of the things that is at the heart of the matter with the D. So you don't have the K label. And that's related to the fact that the world volume is just a point. Like, okay. And then you need to actually be careful about the numbers. What is the volume of the gauge group? It actually has a 2 pi over G naught. Why? Because the interaction term has a G naught times a trilinear coupling. So if the matter field, the wave function needs to multiply by e to the I times 2 pi, there needs to be a G naught here to compensate for the fact that an infinitesimal gauge transformation has a G naught in the transformation law. And the other thing we need is remember that we've had to compute this n times t to the 1/2, because right now this GO, we cannot relate it to the matrix model. It's just some other constant from the string theory. So then we use this, let's say there are various arguments for this equation 51, but we can think about the tachyon condensation solution and take the fact that tension is 1 over 2 pi squared GO squared. So this coefficient is important in getting the right answer. Okay, so how much time do I have? Negative. Sorry? Okay. Okay, so we had a lot of discussion, so it's good. Yeah, okay. So this was f of, so let me just show how we fill all these details. So it's very simple. You have f of t, you write it, this was this original thing that I wrote, it's just powers of q. You write it as some bosonic things minus the fermionic things. So HFs are the fermionic modes, HBs are the bosonic modes. So right now, just think of the original way we did it in Siegel gauge. So let's say these are the states in the Siegel gauge. So log n is integral dt over 2t f of t. And if you take this integrand, the integral of dt over t produces a log. So you get a log of product of the weights of the fermions in the numerator and the product of the bosonic weights in the denominator. That's just this integral dt over t. So that's log n. So n is the exponential of that. So n is the exponential, so you get this 1/2. It actually turns out that all these HFs appear in pairs. So you just put the 1/2 and you just sum over one element of each pair. And there is HB to the 1/2. And now we realize that this quantity is just a path integral. It's a path integral over a bosonic field, HB phi b square, path integral over a pair of fermionic Majorana modes, PFQF, HF hat, PFQF. So this is it. So this is the string field theory path integral, this one at the last line. So we went from a worldsheet expression, which is sort of a single string thing, to a multi-string object. And we rewrote it as just an integral over these various modes. Okay, so what is the problem? The problem, of course, is that one of these HBs is negative or 0, right? That was the problem. So we had a problem that one of the HBs was negative and one of the HF was 0. So how do we fix it? Well, we just fix it by saying for the tachyon, you just have to turn the contour 90 degrees. So that's easy. The P1 and Q1 you replace by the psi integral divided by this volume of the gauge group, like we discussed. And all the other integrals are just fine. So you just keep them like they were. And the tension is 1 over 2 pi squared GO square, like from the previous slide. So now it's done, right? You have n. This is finite. It has an I in it because we turned the contour by 90. This thing has a GO in the numerator. When you take t to the 1/2, that GO is going to cancel. And if you work it out, you have the explicit expressions. You find the exact same results for this n times t to the 1/2 quantity. And notice that this contour that was turning vertical that I showed you in the eigenvalue plane, now that choice is on the tachyon integral. So there's a complex phi1 plane, and you have to pick a contour to integrate the tachyon because it has a negative mass squared. And so there's a one-to-one correspondence between the choice in the matrix side and the choice on the string theory side. Okay, so that's it. And well, I have just a couple of ending comments, but I'm done with the technical part of the results that I wanted to present. Questions?
So t means 1/2 is essentially because it is something proportional to the open string coupling constant.
Right. So we saw that n here has a GO in it.
Yes, but I was just looking to the T, which is one of the
GO
open.
square.
So
Yeah.
this means that it is an open string contribution. essentially.
Yeah, yeah. So the open string action has a 1 over G open square out front, right? So we know that the branes are solutions in the classical open string field theory. So the action of a classical solution should be like 1 over H bar. And the H bar is G open square. So that's why there is this 1 over G open square, roughly.
Concerning this psi integral, I understand that the gauge group is compact, but psi is this auxiliary field, and I don't see why one wouldn't integrate over the whole line of the auxiliary field psi. Not naturally, you know, like I understand that the epsilon, how to say, the gauge group is compact, but the connections are not, right? So the d mu epsilon can be anything in principle. So
yeah, but the division we do in the pathing, so there's a psi integral, which is just a Gaussian. It's e to the minus psi square.
right.
And psi you integrate over the whole line.
Oh, you integrate over the whole line.
Yeah, the thing that's compact is the thing that goes in the wall gauge that goes in the denominator.
All right. Okay.
Yeah, psi is, yeah. So we have, you know, like when we start doing gauge theory, just it's integral d fields over wall gauge. So this gauge group is the thing that has a compact volume. And let me just say why there's a GO that shows up in that thing, because so if we write the open string action in which the coupling constant is explicitly multiplying some trilinear term, so you might have some, this is explained in Ashok's paper, but you can write a trilinear term like this. This is some field, anti-field, and the psi field that I showed. And the gauge transformation is, the rule is you're supposed to take a derivative with respect to xi star, and then replace the xi with the gauge parameter. So the delta psi is proportional to G naught and times the gauge parameter. So if you want the phase angle to be 2 pi, you need the range of the gauge parameter to have a 1 over G open string in it. That's why that's there.
So may I ask one more question?
Yeah.
Just you mentioned at the beginning to Carlo that there is one instanton but can be several holes.
Yeah.
Now, if it's a d instanton, how can you have at the point several holes?
Well, it's some abstract thing, right? It's defined by some boundary conditions.
So this is well defined to have several.
Well, you see, in this case, we don't even have a target space. It was a minimal model on the worldsheet. So abstractly, what it means is that you have a worldsheet theory, you have a CFT, and there are allowable boundary conditions. And we are just studying the various boundary conditions of that CFT.
Yeah. So I kind of remember that the first paper that Ashok wrote on this normalization was in this equal 1 string. Yeah. And there was also an issue about picking the correct left-shot symbol from the contribution of the d-instanton because of the form of the tachyon potential, essentially. That was cubic.
No,
and
he had
here also you have the same.
Yeah, he had the same contour, but the tachyon contour comes in horizontal in the perturbative vacuum, and then you
right.
There's a 1/2 there.
Yes, and here, what is the situation? So here also you have to account for this, or not?
Well, so that goes back to the discussion we were having with Sergey. So the minimal thing you can say is that you have various saddle points in your integration space, and we know what the full one loop factor is around each saddle point, but we don't know what linear combination to take.
Okay, so you're at the moment you are not able to add to this computation the perturbative computation. So they will be related to this problem.
Yeah, even if we add it, right? Like there are 2 instanton, 3 instanton, 4, and it's not known even if that holds the double series, the trans series converges or not. Like, so the non-perturbative solution to these models is I think, to my limited knowledge, is an open problem.
I see. So is the form of the tachyon potential, of the ZZ tachyon potential is not going to help you in this, like it was doing in.
Yeah, because I think we could fix the contour like I showed at the 1 instanton level.
Yeah.
But at the multi-instanton level, we don't know. And even the multi-instanton series is still just an asymptotic series. So, the situation is much better for unitary matrix integrals. So there's a version of matrix integrals where the eigenvalues lie on a circle. So there, the integration contour is just compact. And there you can take a double scaling limit. And there you have control over both the asymptotics as the string coupling goes to plus infinity and minus infinity. So then you can fix a unique solution to these Penn-Levy equations. Whereas here, the real issue is that the contour of integration is sort of non-compact. It goes from minus infinity to plus infinity. And you just have to define that contour well like that. So there are extensions of the result, as I mentioned in a paper in June. We extended this to the P prime comma P minimal string theory. And the string theory computation here was straightforward. So now this gauge group, if you have little n instantons on top of each other, you just have a volume of un instead of u1. That's also compact. That showed up in Sergey's talk as well. So you can put any number of instantons of any type as long as this number is not scaling with n. And it again matches. And this group ul plays a role if L was the total number of instantons. And this is just one ongoing work. We are done with all the computations. We just have to write it. I have to say that on all of these papers that Ashok was writing, everything matched to the dual results, or everything was nice, except this one point. In this paper from December of 2020, there was found a mismatch between two computations of the annulus one-point function. So now we are not talking just about free energy, but about a one-point function on the annulus, which is relevant for the next order computation of the BRY that Balthazar, Rodriguez, and Yin did. So the matrix computation is just correct. It gives you something. The other was a string theory computation in which you do sort of the bulk moduli space integral numerically. That was done by BRY. And then the boundaries of moduli space, you deal with string field theory. So Ashok computed that. And he just found a mismatch. Like the matrix model was predicting some number is 0. And this numerical integration plus the SFT analysis was giving to be 1/2. The point is the C equals 1 model is slightly more complicated because you have a free boson on your worldsheet. And because of that, there's a translation 0 mode and time and so on. So what the idea we had was to simplify this and study the same quantity in the C less than 1 theory. Because at least you get rid of this annoying boson. Like you don't have to worry about any mistakes coming from that sector. And what we find is that if you do the SFT analysis, two good things happen. One is you don't need to do any numerical integration over a moduli space because the vertex operator was actually a total derivative because of the Leoville equation of motion. So because this one-point function that you're putting on the annulus is a total derivative, you only get contributions from the string field theory on the boundaries of the moduli space. And there again, you found a mismatch between the matrix computation and the SFT. So, that narrows it down. That says that, okay, the SFT computation must have had a subtlety. And we indeed sort of found that. So this is work with Pronobesh Meiti as well, together with the previous collaborators. You compute this annulus one-point function in C less than 1 string theory, does not require numerical integration. And it allowed us to isolate a subtle issue in like appendix D of this paper by Ashok. Like there was a 10-page appendix in which he was computing actually this relation between, this 2 pi over G naught. So there's a computation that gets a field dependent correction. And that was a computation of a 4-point function with 1 closed string and 3 open strings. So that's a 2-dimensional moduli space, and that had a subtlety in it. And you fix that, you realize there's a subtlety there, and you fix it, and now those results are matching, both in the C equals 1 and C less than 1. Okay, and here is Pronobesh. You heard from him as well, but he's also applying for postdocs this fall. And okay, thanks. Okay, do you have any final questions or comments? Sergey has a comment. Can you pass the mic?
this last result, which you presented,
Yeah.
you said it's 1 point function, the annulus of which operator?
Or let's say of the cosmological constant operator of e to the 2b phi.
And another question, what happens if you consider other ZZ boundary conditions labeled by MN?
Right, so we computed it in this paper. So in this paper, we were completely general. You take p prime comma p minimal string. You put L1 instantons of type 1, L2 instantons of type 2. Type means the different ZZ branes. So you take, yeah, L1 ZZ branes of type 1, L2 ZZ branes of type 2.
What is the corresponding instanton on matrix model side?
So I showed this effective potential, right? This one that had multiple humps. So you put 3 on the first maxima, 5 on the second minima, 7 on the third.
So you want to say that the extrema are labeled by 2 integers?
Yeah, in general. In the 2 comma p, they're labeled by 1 integer. So those extrema of the effective potential are precisely the ZZ branes. For example, you could compute the ratio of the heights of those extrema. And the bootstrap solution given by ZZ matches the heights, the relative heights of the minima and the maxima. Right. For the 2 matrix, it's harder to see what the other direction is, but you know there is this whole algebraic geometry and stuff, so you get those 2 integers out. Yeah. UG has a question.
So on your string series calculation, you calculate the empty annulus, right?
Yeah.
In the open string channel.
Well, you could compute it in either channel, but the expressions I wrote were in the open string channel.
Okay. So which part depends on so it has been not to do with the Leoville sector and minimum model sector, right?
Yeah.
So which part of the calculation depends on those information from those sectors?
Especially well, it depends what the zero modes are.
P, right?
Sorry?
The final result depends on P, which means that something depends on the.
Yes, something depends because we have those the low-lying modes, the L0 equals -1 and L0 equals 0.
Yeah.
But there's this whole tower of modes.
Okay.
That whole tower depends on the actual theories.
I see. So that entered the calculation. So I think you didn't.
Yeah, I wrote it here in this all other integrals.
All other integrals, I see.
Because that corresponds to, there is this infinite sum here. And the k equal to 0 term is the 2 leading terms. So the k equals 0, you see here, it's just e to the 0, that's 1, minus q. So multiplied by this, that gives you the 2 0 mode. But there's a whole infinite series here. So there is this infinite product that you need to do.
Yeah, that's complicated, but there's no subtlety.
There is no subtlety in those because they are massive modes, and these values, the spectrum you see depends on P. So the spectrum of L0 depends on P.
Then I assume that this calculation can be reproduced by crossing channel by calculating the boundary state.
Yeah, that was done already by Emil Martinek and some other people.
Yeah,
in the early days.
Right? Yeah. So, but in open string channel, so there's a subtlety in the zero modes and tachyons that can be safely or unambiguously fixed by this calculation.
Yeah.
Very good.
Yeah. In principle, you could have had a divergence from the t equal to 0 side as well.
Yeah.
But you don't because these theories don't have a closed string tachyon.
Very nice. Thank you.
Okay. Are there any urgent questions? We also have the discussion this afternoon, so if you are thinking of anything, just keep it in mind and you can ask later. Okay.
Okay.
Thank you. Let's thank him again.